Okay, hi, this is Speak Tuition, and this is a quick review on the chapter of graphs. So graphs are a very fundamental and important chapter in A-level math, and it is basically like equation or function that you have encountered before. It's a visible representation of relations between two or more variables like x or y. Usually it's representing x or y lah, but although there are some rare cases where it's not. But essentially, you have two axes, and usually the horizontal axis we just call x and we just call y. So on a graph, we have several important things that we need to take note of. One is the axis intercepts, then there's the stationary points, asymptotes, points or lines of symmetry, and finally, for some questions, you will need to take note of the domain and range. Alright, we'll talk more about what domain and range are in a moment. But basically, starting off with axis intercept, we see that axis intercept are basically when a graph cuts the x or y axis. In these cases, let's say for this x-intercept, the x-intercept is basically when your y is 0, right? So we can substitute y equals to 0 into an equation. For example, if you have an equation that looks like this, y equals to 3x plus 2, we just sub y into 0, y equals 0 in it, and we can find what's the x-intercept. Vice versa, the y-intercept is similar because this is basically when the x is equals to 0. So similarly, we can substitute x equals to 0 into an equation to find what is the y-intercept. So that's for axis-intercept. Very important to take note of when you are sketching or drawing graphs. Next is the stationary points. These are also known as turning points. They have zero gradient. We notice that here, let's say for this, we have a minimum point, which is the gradient going down, then gradient is 0, then gradient going back up, right? And we also have a maximum point where you see that there's another 0 gradient here. And finally, an inflection point, which the gradient is going up, gradient is positive, becomes 0, then goes back to the same direction. Okay? There are actually two types of inflection point. There's one more inflection point that do the other way around, which is going down, then goes back, becomes 0, goes back down. Okay? So it is important to mark out these points as well. Okay, so usually the stationary points that you have to draw are basically your quadratic equation stationary point. So for quadratic equation, you can do the complete the square form, or some schools teach them as the vertex form, and you can find what is the stationary point that way. You can find what's the turning point, basically the vertex. Okay, so if you're already very familiar with differentiation, you can also use that to find the turning point, to locate what is the coordinates of the turning point for you to label on your graph. Okay? Moving on, we have asymptotes. So asymptotes is when a graph gradually approaches a straight line when x or y increases to infinity. Alright, a very simple example that I'm going to just throw out here so it's easier to visualize is 1 over x graph. 1 over x graph looks like this, and we see there are two asymptotes, one x asymptote and one y asymptote, basically horizontal or vertical asymptote. So here we see that when 1 over x, right, when the x goes to very large, like in this direction, when in this direction, okay, 1 over x, when x goes to very large, 1 over x becomes very small, but it never ever hits 0. No matter how big x becomes, 1 over x will just become smaller, but never 0. And this is one of the asymptotes. In the second case, because we see that 1 over x is a fraction, right? And when x is equals to 0, your entire fraction becomes undefined because you can't divide by 0. So that forms the second asymptote, which is the vertical asymptote. So vertical asymptotes basically takes on basically the equation of a vertical line, x equals to something, in this case x equals to 0. And horizontal asymptotes takes on also a horizontal line, which is y equals to something. In this case, it's y equals to 0. When I mean something, I meant a constant, okay? So in this example, it's the two asymptotes is horizontal and vertical respectively. but it can also take on a oblique asymptote in the sense that your asymptote can be actually like y equals to mx plus c. More on this later when we talk about hyperbolas. Okay, so for a general equation, y equals to px over qx, where px and qx are polynomials, we can actually carry out long division such that we can write it as this form, where you have a function outside and another fraction. This is a proper fraction lah. In this case, it's a proper algebraic fraction. So usually what happens is you will have two asymptotes. One is fx. One is at the roots of the qx. Why? Because when you have the roots of the qx, right? We start off here. Look at this thing. When we have roots of a qx, your qx goes to 0. Then your fraction goes to infinity. This is basically similar to this asymptote over here. Your 1 over x goes to infinity, therefore it becomes undefined, therefore you have an asymptote. Okay? So the second thing may not be so obvious, but why is fx also an asymptote? Because when this fraction becomes very large, or rather when x becomes very large, this fraction tend to become very small because this is a proper algebraic fraction. After you do the long division, this rx over qx becomes a proper algebraic fraction. Fraction. What this means is that the order, that means like what's the highest power of rx, becomes smaller than what's the highest power of qx. And this means that as x increases, this fraction tend to become smaller. So example of having a smaller power, right, can be seen here. What I mean by having a smaller power is like this. So we see that when x becomes large, x squared becomes even larger. So eventually when x becomes very large, this whole fraction becomes very small. It's as good as 0. So when x becomes very large, goes to infinity, now there's a typo here, it becomes very large. This entire fraction goes to 0. And when it goes to 0, we are basically left with fx. But we know that this fraction never actually goes to 0. It just becomes as close to 0 as possible. It never actually equals to 0. So fx becomes an asymptote. This is very important because in the hyperbola part, we need to use this result as well. But just keep this in mind, and try to understand why fx is also an asymptote. Okay? So this is basically to summarize, this is the how to find asymptote for a general algebraic fraction. Next important thing is the line or points of symmetry. So these lines of symmetry are basically lines where you can reflect the graph and still get the same graph. So earlier we have an example of 1 over x, right? 1 over x. If we reflect this 1 over x about the origin, we see that we get the same graph. Another example would be maybe 1 over x squared. Okay, 1 over x squared looks something like this. Not drawn very well, but you see that if you reflect it about the y-axis, we still get the same graph. Other possible graphs that we encounter with line of symmetry is that, like sine graph has a point symmetry, cosine graph have a line symmetry about y-axis, okay, so on and so forth. You can go and sketch them out and try and reflect them yourself to make sure that double check, okay? So when we have symmetry about x, when we have symmetry about the x-axis, it means that all the y values flip. So this is what happens. Your fx, which is the y, equals to minus fx. Symmetry about y, this is another typo. Symmetry about y is when all your x coordinate flips. So your input basically flips to the other side. And this flips you about the y-axis. Basically, it's like, in this case, we see that when we flip the input, when all our x value here, these are negative x, becomes positive x, we still get the same value. Okay? So symmetry about y is when this is true. And yeah, this is how to think about it in word form. Okay? In any case, symmetry about the origin will look like this. We can think of it having the same equation when both x and y are changed into minus x and minus y. Essentially, it's like flipping both x and y axes. Okay? So note that symmetry about y is the same as having an even function. Even function just is the same definition. And symmetry about origin is the same as having an odd function, which is again same definition. Okay? So like for example, sine is actually an odd function and cosine is an even function. Okay? Even an odd function usually not that tested, but good to know. Okay? So next, domain and range. These are the limitation to the regions where the graph exists. So domain actually talks about the input, what are the valid input, and the range is the valid output. So for example, for x square graph that looks like this, the domain is all real x and the output range is positive values. Okay? Finally, we have a special type of equations which is known as the parametric equation. So in this case, x or y are usually represented in a third variable, often like t, u, v, etc. This third variable is a parameter that helps in expressing x and y. And because you see it's a parameter, right? Therefore it is called a parametric equation. Not a very nice name, right? It sounds cool, but it's not that cool. Anyways, so this type of parametric equation is usually solved using GCs or like your GC graphic calculator, or you can just substitute. So for example, we can do a parametric equation that look like this: x equals to t squared, y equals to t4 minus 2t squared, and we can just substitute the t squared in this case. This is a very simple example. Not all the example will be this simple, but because we can substitute t squared, we basically see that this is x squared minus 2x, and then this is equals to x minus 2, and therefore we can plot the graph like this: y and x. This is 0, this is 2, quadratic equation. Okay, so we can do substitution to find how the two are related. Next, we have conic sections. So conic section is one entire class of functions that are basically cut out from a cone. So when we have this is a very cool, okay, maybe not so cool because it's quite difficult, but basically from this cone shape, we are able to obtain 4 different types of graphs, and all of them originating from the same family. They are actually all the same family of curves, of graphs. Okay, so by cutting a plane into this cone, we can actually get many different types of graph. So we imagine the cone is just a hollow. The cone is hollow, and when we cut it, whatever is on the surface is the graph that we see. So if we cut it horizontally, we get a circle. If we cut it slightly slanted, we get an ellipse. If we cut it even more slanted, we get a parabola. And if we cut like this, and if we cut it even more and such that it cuts the other side of the cone, the upper half of the cone, we get what is known as a hyperbola. Okay? So you will imagine that your circle just looks like a circle, your ellipse will look something like this, and your parabola will look something like this. Your hyperbola will look something like this. Something like this. Okay? In any case, the general equation of the conics can be represented like this. Important equation, you don't necessarily have to remember this, but try to understand how all this work. Okay? How y, basically is there's a y square, there's a xy, there's a x square. You have up to the second order. All these 3 terms, the first 3 terms here are second order terms because there is two variables multiplied. These 2 are the first order terms, and then there's a constant term. Okay? To determine the type of graph, we can check these conditions. Please go and remember the conditions. For circle, a must be equals to c, so the coefficient of the x square and the y square must be the same. For ellipse, a and c have the same sign. It is then not hard to see that the circle is a special case of the ellipse. because if A equals to C, A and C already have the same sign. So circle is a special case of ellipse. Then we have parabola, where A equals to 0 or C equals to 0. In this case, we just get, if A is equals to 0, we get a parabola that looks like this, like up or down, happy face, smiley face. If C is equals to 0, then we get a parabola that is sideways. I believe you don't really encounter this type of parabolas, but well, just for your knowledge sake, okay? And finally, for hyperbola is when A and C have different signs. Okay, that's all. It's like the opposite of ellipse. Okay. So with that out of the way, we start doing more details for each of the type of graphs. So for circles, the general form is x minus h and y minus k equals to r squared. One way to look at it, this may look quite daunting, but one way to look at it is when you have x minus h, right, we're basically saying that we are setting like h as the point of reference, and we are looking at x around h. And same thing for y, so we are looking at y around k. X, that is hk. And we notice that there's a square. So that means when x around k, x around h squared plus y around k squared is equals to r squared, what does this remind us of? This reminds us of Pythagoras theorem, right? So that means the hypotenuse of any point from this hk must be r. Then what do we get? We get a circle, right? Circle with radius r. Okay. So this very complicated looking equation actually is just a hypotenuse, like Pythagoras theorem, that tells us, oh, you form a circle with radius r. Okay. So by rearranging, right, axis intercept can be found. So remember just now we said that x-axis intercept is when y is 0. Y-intercept is when x is 0. So you just go and set the x or y to 0 and then go and work it out. You should be able to get this. Remember when you do square root, you must have the plus minus, because both plus and minus when you square give you the same square. Okay, so when you square root it, you must consider both the plus and minus. Notice that I say if applicable. Why if applicable? Because if the axis is here, then there won't be any, there just won't be intercept, right? If your axis looks like this, then there's no intercept. So you must check whether if it's applicable. For stationary point, it goes without saying that it is h, k minus r, and k plus r, because it's a circle. The circle with radius r. So if the center point is hk, then the stationary point on top, this will be h, k plus r, right? And the bottom is h, k minus r. Okay? So yeah, that's for stationary point. Because it's a circle, there's no asymptotes, because it doesn't approach any value specifically. And because it's a circle, you can cut it in any way that as long as it cuts through the center, you have a line of symmetry. You can cut it in any way as long as it cuts through the center. Finally, the domain and range is simple because it's a circle. You plus or minus the r. Okay? So basically, this is the domain, right? Let me change the color. This is the domain where you have h from h minus r to h plus r, and your range is k minus r to k plus r. Okay? So that's for circle. Next, we have the more general form of a circle, which is ellipse. So general form of an ellipse looks like this. It looks actually quite similar to the case of a circle, except now you have a divide by a square and divide by b square. The way I think about it is that now you are scaling your x and y direction. So you originally have a circle that looks like this, but then you choose to, oh no, this is a circle. But then you choose to scale your x or y differently. So let's say your x you scale like this, then your y you scale like this. Then you end up having a funny circle instead of a proper circle, right? And actually, this way of thinking of it actually should be pretty correct, because from the center, this is actually your A and this is actually your B. Okay, so your A is like the x radius and your B is like the y radius. Okay, so ellipse and circle are very closely related. This is basically how you think about it. So for axis intercept, go and try and like just substitute your x or y equals to 0 and see if you get this. This should be correct. I don't think I made a typo here. Just substitute in and see if you get this. For stationary point, same thing. Stationary point is on top and below of the the center point. So naturally, you just need to plus or minus b, since b is like the so-called vertical radius. Okay. Note that I really like wrote the inverted commas because this is not a radius, but yeah, it's kind of like a radius. Okay. Alright, so next we have asymptotes. There's again no asymptote because this ellipse is not it doesn't approach any value in particular. And unlike the circle where you have infinite number of lines of symmetry, here there's only two ways you can cut it. You either cut it this way or you cut it this way. Then other ways do not give you a asymptote. Other ways do not give you a line of symmetry. Okay? For domain and range, same thing. We can see that the domain is this much. So since the center is hk, we see that the domain will be h minus a to h plus a. The range will be k minus b to k plus b. So this is k minus b, k plus b. Alright. Now next, we have parabola. Parabola is something that I think is very familiar to all of you, but I'll do a quick recap. So there are three forms to a parabola. One is the standard form, which is shown here, ax squared plus bx plus c. Then there's the factorized form, which is, you can write it as a multiplied by x minus alpha and x minus beta, where alpha and beta are your two roots. And finally, we have completed the square form, which some people call the vertex form. Okay. What is important is I will just draw a quick sketch to tell you how each of them relates to the quadratic graph, because it's super important actually. Please go and understand like how quadratic graphs work, because it really is super important. I think it's like one of the most important things in A levels. So this value, the y-intercept is c. So this is c. The two x-intercept is alpha and beta, which is here. Okay, this turning point here is given by hk, which is here. And one thing to take note, right, is always take note of the sign. Okay, this is minus alpha, but here when I write it down, this is just alpha. This is minus beta, but here when I write it down, it's just beta. Here is minus h, but when I write it down, it's just h. Here is plus k, and there's no negative sign here. Okay, so same thing here. Here is plus c, there's no negative sign here. So this is basically how you sketch a parabola. Very important to know all this. And of course, it goes without saying that the line of symmetry is down this line here in the middle, where you have x equals to h. Okay, so yeah, so the general form of the parabola is, this general form can be taken from above with the general equation of a conic. But there's also the other form where you have like x equals to y squared plus y plus c ax squared, ay squared by plus c, and this will give you the other direction, the parabola in pointing in the x or y direction. Okay, generally it's not very tested in A levels, but even if it is, just plug it into most likely it's a GDC question, like a graphic question, calculator question. Don't have to worry. Alright, so we can also see that the quadratic formula will give us the axis intercept like this, if applicable, because we know that there are possibility where you have no axis intercept and y equals to c. Okay, y equals to c is also a axis intercept. The stationary point is given by hk, as you have seen in this sketch here, and the point of line of symmetry will be x equals to h. Alright, for domain and range, the domain is all real number and the range is anything above k or below k. Okay, so here I actually didn't specify properly, but this is if a more than 0, then k less than equals to k more than or equals to y if a more than 0, less than 0, yeah. So basically, if it's a happy face, then this is k and your y value can take anything above. If it's a sad face, then this is your k and your y value can take anything below. That's basically all. Okay, so next, hyperbola. Hyperbola look like this very cool, like double-sided parabola, except it's not a parabola. And there are two ways that it can manifest. One is I'll just call it the type 1 and type 2. So notice the color. So type 1 is the red one. The type 1 red one just like left side and the right side. Okay? So in that case, in the case of the type 1 parabola, you don't see the blue color stuff. You don't see the blue color stuff here. You don't see this thing, you don't see this thing. So notice that here is x squared minus y squared. And in the case of blue one, the blue graph that looks like this, okay, you have y squared minus x squared. Alright. And here, this distance here is a, and this distance here is b. Okay? So, this type of graph is very cool because there are two asymptotes. You can draw one asymptote like this, and you can draw one asymptote like this. Okay, there are two asymptotes that lies in it. Not very well drawn, but yeah, you get the point. So here we can still find the axis intercept by equating x or y to 0, because there's quite a few different ways you can intersect the x-axis. So yeah, you can either be the red line intersect the x-axis, or you can be the blue line intersect the x-axis, and it's not super straightforward. Just go and do it yourself, this algebraic manipulation. Okay, for stationary points only exist for this type of blue graph lah, because if it's a red graph, then you don't really have a stationary point. So it's this point here and this point here. So these 2 points is basically hk plus b and hk minus b, because this point in the center is hk. Surprise, because, well, I mean, so far a lot of it has been hk, right? Like our circle center has been hk, our ellipse circle has been hk, our center of the parabola has been hk. So it's no surprise because it's like how far we shift our graphs away from the center, right? Okay, so that's the stationary points. For asymptotes, there are two asymptotes, as we have mentioned. One is the pointing upwards, one is pointing downwards, basically 2mx plus c graph. So this one, we have a plus minus b over a x minus h plus k. What this is that it's just we are taking the center point, and then we slap a gradient on it, which is b over a. The gradient is equals to b over a, and plus k. K is the y coordinate. Okay, so how do we remember this? Just remember that you are shifting to x minus k and x minus h and plus k. This is the coordinate that you want to pass through, and then the gradient is b over a. B is the y, b is the scaling for the y, b is like the scaling for the y, and a is like the scaling for the x. So it's like changing y over changing x, right? So it's b over a. Alright, so that's how I would remember it. In any case, the line of symmetry the point of symmetry will be at the center. That's all, right? For domain and range, there are two possibilities for type 1 and type 2, but it's basically just the same. You see that for type 1, the red graph, the domain will be anything here and anything here. And the range covers all real number. And vice versa for the type 2 graph, the blue graph, okay? So that covers the gist of the conics graph. But there are other special cases of hyperbola which are written here. Okay, I'll briefly go through them. They are quite important actually, but we have already talked about them here when we talked about asymptotes. So yeah, this will be quite brief. We see that when we have a rectangular hyperbola, what it means is that we have a horizontal and vertical asymptote that looks a bit like our x square graph. 1 over x graph. So there's a general form where you have ax plus b over cx plus d. This can be written as k plus p over x minus h, where k is equals to h is equals to this and k is equal to this. Notice how the hk appear again, because it's useful. Hk basically usually this represents like where do you shift the graph towards. Next chapter is on transformation. You can see why I always write it in terms of hk, because it's basically like shifting the graph to the position hk. Alright, so now you may wonder, there's another p over here, right? There's a p over here. Why I never write the p? Because p is just a number, and this p is I got it from, I mean, it's just a number that is from all the manipulation. If you want to write it in terms of ABCD, this is equals to something like AC over AC multiplied by BA minus DC or something. But in practice, when you do your manipulation, just do it. Just multiply them, and you will just get a single number. You won't be a funny thing. It won't be like a funny with x squared or something in there. Okay, so yeah, basically this will give us a 1 over x graph at the HK position, center at the HK position. HK as in the coordinate h, comma k. So we see that the rest of it is justifying where's our two asymptotes. Where's our two asymptote? If your 1 over x graph is centered at HK, then naturally your asymptote will be x equals to h and y equals to k, right? So yeah, if you're not convinced by me saying that the 1 over x graph shifted, just follow through this argument and it should be convincing. Okay, so here the rest of this is talking about the five important things that a graph must have. One thing to take note is that, right, I didn't specify it, but except the domain and range, right, is except undefined points. So if any of the x or y is undefined, right, you cannot use it. So usually it's the x equals to h and y equals to k. Those two are not in the domain and range. But yeah, just take note, when you write down your domain and range, please remember to exclude those two. I didn't write them out properly. Yeah, okay. So for hyperbola with one vertical and one oblique asymptote, this originates from a general form that looks like this. When we have a quadratic term on top and a linear term below, what happens is there will be a px plus q outside after the long division or polynomial division. When we have a px plus q, then it's not super clear how the graph will look like, right? But actually we know that when x is very large, r is just a number, right? So when x is very large, this fraction just tends towards 0, because a very large number in the denominator with a number on top, eventually the whole fraction just goes to 0 when x is large enough. Okay, so that means when x is large enough, your graph basically looks like px plus q. This is basically to justify why y equals to px plus q is an asymptote. And when h is going towards when x is going towards h, we see that again this fraction becomes undefined, and therefore x equals to h is another asymptote. So how this graph will look like, right, is something like this. It will look something like this. Let's say this is px plus c. Okay, so this can be x equals to h, and this is px plus q, and the graph will look something like this. Maybe like this. Okay. Alright, so in this case, right, there's actually two stationary points. One is here and one is here. Okay, and these two stationary points can be given by this and this. So these points look very hard to remember, right? But don't have to remember. Usually when you have this type of graph, there are only two scenarios. One is you are using your graphic calculator. The second one is you already learned differentiation, so you know how to find your minimum and maximum point. So how I found this was through minimum and maximum points, like through differentiation. So it's quite unlikely that you need to remember these values in particular. Okay. Notice how there's a condition attached here. If r is less than 0. Why if r is less than 0 then there's a turning point? Because why if r is more than 0 then there's a turning point? Because if r is less than 0, right, your graph look like this. Then if your graph look like this blue graph, then if your graph look like this, right, you won't have a turning point. Simple as that. So yeah, so that's about right. Asymptotes, we already talked about it. There are two asymptotes involved here. One is an oblique asymptote, the px plus q. One is x equals to h. For points or lines of symmetry, usually there's none. Okay? So don't have to worry too much. Yeah. So next we have domain or range. So if r is more than 0, we see that there's a gap in the range. We see that there's a gap. Like the range will not have this gap. Not in range, right? So this would, for that you just need to find out your coordinates, your, what do you call this, your minimum point and maximum point, and that would tell you what is the range of r that just doesn't exist. Okay, so with that we basically cover the three types of hyperbola. So hyperbola is a very new thing to A level, so it's, don't be scared of it. Just think of it as a very cool graph and that relates x or y together, and there are a lot of asymptotes involved. Yeah, okay. So with that, we can move on to other forms of functions. We've been talking a lot about fraction functions with like x squared on top or x on top with x below. So to properly define it, it's more like they are basically a fraction. They are a fraction of two polynomial functions of form px over qx. These are polynomials. So these domains, right, typically cover all value of x except for the roots of qx, because q, again, when your denominator is 0, your whole function is undefined. So roots of qx is not in the domain. Okay, when the degree of px is higher than qx, then the fraction is improper. So for example, this graph over here, right? This graph over here, you see the degree of the top. The degree of the top is 2, the degree of the bottom is 1. Basically the highest power, highest power of the on top is 2 and highest power of below is 1. So in that case, the fraction is considered improper. So when it's lower than q, then it's proper. So try and make it proper. Okay. So periodic function is another type of function that you will encounter here and there, but mostly in the form of trigonometric functions. So for example, we have a sine graph, right? Let's say we have a sine graph that looks like this. What a periodic function really means is that, let's say we have fx here, fx1. We see that when we add a certain value here, fx1 plus t, we get the same number all the time. Okay, for no matter what is your x1, when we add another period to it, or a multiple of a period, we still get the same thing. So what I mean by multiple of a period is, let's say the graph continues somewhere, then this one is fx1 plus 2t. You still get the same function, right? You still get, sorry, not same function, you still get the same value, right, of fx1 plus 2t. So that's what I mean by saying that the values are repeated over a period, and fx is equals to fx plus minus t, where t is a period or multiples of the period. Okay? The function needs to be defined by having all the values within one period, but one period is enough. You don't need 3 periods to define the function, because, well, one period just tells you all the values within one cycle, right? For A levels, the periodic functions we deal with is just sine, cosine, tangent. Should be only these 3. Oh, I mean, there's always the inverse of them, the cosecant, secant, and cotangent, the cotangent. So, but other than trigonometric functions, we don't really deal with other cyclic functions in A levels. Last but not least, we have the piecewise function. So piecewise function, right, is basically when we have multiple functions pieced together through different x domains. Okay, different x domains. So for example, we can have a, let's say we have from 0, this is x0. So from x next, let's say we have a function x equals to x squared when x is less than 0, and x when x is more than 0. So when x is less than 0, you get a quadratic graph that looks maybe something like this. Okay, maybe look something like this. Something like this. Then when x is more than 0, you get a x graph. Y equals to x graph. Then look like this. Alright, so notice how in this case the domain, right, is x less than 0, x more than 0. So there is no, the domain does not include x equals to 0 itself. So then you need to draw open circle here. Open circle means that that point is not included. Okay, so you must be careful about all this. Another example that is stated here is the Heaviside step function. Here I'll just do the example lah. If you want to try yourself, then pause the video and yeah, just pause the video. Okay, so I hope you tried the example, and what the Heaviside function is basically saying when x is less than 0 is 0, and that means your graph looks like here. Do we include x equals to 0? We don't, because this is a equal, not a less than or equals to. Sorry, this is a less than and not a less than or equals to. Therefore, we draw open circle here. However, when x becomes more than 0, it jumps immediately to 1. And this is a more than or equals to, so this must be a solid circle, and then we continue. So this is this is known as a Heaviside step function. And essentially this is like what happens when you switch on a switch, right? The electricity going to your light bulb, for example, just instantly jump from 0 to some unit. Okay, in any case, this is the chapter for graphs. This is quite a heavy chapter because there's a lot of graphs, a lot of information to take in. In any case, I hope this video helped you for your revision, and happy studying.